Well, to finish up this section, let's just do one more example. We'll recall from chapter 1 in sequences, we know that if the sequence AN converges to the real number capital A, and if every term in the sequence is greater than or equal to 0, then the new sequence created by taking the square root of every element, the radical of every element, that sequence is going to converge to radical A. Well, similarly, if we're dealing with functions, take function f with domain capital D and going into R. If at some x naught, the real number, the limit as x goes to x naught of f of x is the real number capital L, and f of x is not equal to 0, greater than or equal to 0 for all x in the domain of the function, then the limit of, as x goes to x naught, of radical f of x is equal to, as we would expect, radical capital L. Now, all this function is you just take the expression for f of x and you put a radical over it. That's all we're doing. Okay, well, let's look at an example. And we're going to try to use as soon as possible the previous theorem we looked at, 2.5, I believe. Nope, it was... Oh, actually, it wasn't a theorem. It was, we talked about in the previous video, just kind of some mathematical facts. So, we're going to start with f of x being this function, radical 5 plus x minus radical 5 over x. And the question is, does the limit as x goes to 0 of f of x exist? The problem is that 0 is a 0 of the polynomial on the bottom. If x equals 0, we get a 0 on the bottom. So our previous discussion, we didn't address the zeros of the polynomial on the bottom. And by the way, we wouldn't call this a polynomial on top since it has a radical in it, but so we have a problem. And notice that if x is approaching 0, the denominator is approaching 0, and also the numerator would be approaching 0, because this would be approaching radical 5 minus radical 5. Well, there's a fairly simple solution just using basic algebra of square roots. Let's make a note, because right now we can't use that previous discussion since this is approaching 0, has a limit of 0. So let's take 5 plus x minus radical 5 over x. Well, that's equal to radical 5 plus x minus radical 5 all over x times 1. And the way I'm going to write the 1 is as a fraction where I take what's called the conjugate of the top. The conjugate of the top is just what you get when you replace this minus with a plus sign. And so I'll multiply the bottom and top by radical 5 plus x plus 5 over x times radical 5 plus x plus 5. Oops, sorry. I did the multiplication already there. So I'm multiplying this. This is just equal to 1. So it's not changed. It's an equivalent expression. Well, what we get after doing that is, let me do the bottom first. We would get x times radical 5 plus x plus 5. But on the bottom, I'm going to kind of do all the algebra in my head here. What do we get when we multiply something by its conjugate? Well, if you FOIL it out, the outer and inner terms just cancel each other out. So all we're left with is, in FOIL, would be the f and the l. So we're going to take the first times first, which is radical 5 plus x times radical 5 plus x. That's 5 plus x. And the outer and inner cancel each other out. And the last thing that we get, oops, I made a mistake here. That needs to be a radical 5. And that needs to be a radical 5. So this also needs to be a radical 5. Like that. Okay, so the outer and inner cancel out, and the last is negative radical 5 times positive radical 5, which is a negative 5. And that gives us, let me keep going to the right here, that gives us x on top, the 5 and negative 5 cancel out, and gives us x times 5 plus x plus radical 5 on the bottom. The x's cancel, and we get 1 over 5 plus x plus radical 5. So therefore, the limit as x goes to 0 of f of x, which is this guy right here, is equal to the limit as x goes to 0 of this guy right here, which is equal to the limit as x goes to 0 of the top, which is a constant 1, over the limit as x goes to 0 of the bottom function, which would be radical 5 plus radical 5. Or 1 over 2 radical 5 for the final answer.